What if I told you that right now, as you're watching this, you're surrounded by forces so powerful they could destroy entire solar systems in seconds? What if the most powerful thing in the universe isn't what you think it is? Not black holes, not supernovas, not even the Big Bang itself. Today, you're going to discover something that will fundamentally change how you see the cosmos and your place within it. You see, when we talk about power in the universe, we're entering a realm where numbers become almost meaningless. The energies involved are so vast, so incomprehensible that our human brains simply weren't evolved to grasp them. But that's what makes this journey so incredible. And if you're fascinated by the universe's biggest mysteries, I'd love for you to subscribe to this channel and join me on this journey. Your support truly helps this channel grow. We will always explore the cosmos together. Now let's begin. Let's start with something familiar to put this in perspective. The most powerful nuclear weapon ever detonated by humans was the Tsar bomber, tested by the Soviet Union in 1961. It released 50 megatons of explosive energy, enough to level entire cities and create a mushroom cloud that reached 42 miles into the sky. To us, that seems like the ultimate expression of destructive power. But here's where your mind starts to bend. The Sun, our friendly neighborhood star that makes life on Earth possible, releases the equivalent of 1 billion Tsar bombers every single second. Every second. And our Sun is actually a relatively small, calm star, what astronomers call a yellow dwarf. It's like comparing a gentle candle flame to the cosmic infernos that rage throughout the universe. This incredible energy comes from nuclear fusion happening in the Sun's core, where temperatures reach 15 million degrees Celsius and pressures are 250 billion times greater than Earth's atmosphere. Every second, the Sun converts 4 million tons of matter directly into pure energy through Einstein's famous equation, E equals mc squared. This process has been going on for 4.5 billion years, and it will continue for another 5 billion years. But even our Sun's tremendous power pales in comparison to what we find elsewhere in the cosmos. When massive stars, those at least 8 times heavier than our Sun, reach the end of their lives, they don't go quietly. They explode in events called supernovas, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. The Crab Nebula, which you can actually see with a small telescope, is the remnant of a supernova that Chinese astronomers observed in the year 1054. The explosion was so bright it could be seen during daytime for 23 days. And this happened even though the star was 6,500 light-years away. Imagine an explosion so powerful that its light outshone the Sun from a distance of over 38 quadrillion miles. Recent observations from the Hubble Space Telescope and the newer James Webb Space Telescope have revealed supernovas in distant galaxies that challenge our understanding of stellar physics. In 2016, astronomers discovered a supernova called Assassin 15 Lechi that was 570 billion times brighter than our Sun at its peak. That's 200 times more powerful than a typical supernova, forcing scientists to reconsider what's possible when massive stars die. But we're just getting started on our journey up the cosmic power scale. In 1967, a graduate student named Jocelyn Bell Burnell discovered strange, regular pulses of radio waves coming from space. At first, she and her advisor thought they might have found signals from an alien civilization. They even nicknamed the source LGM-1 for Little Green Men. What they had actually discovered was a pulsar, a neutron star spinning hundreds of times per second. These are the collapsed cores of massive stars that have gone supernova, compressed into a sphere just 20 kilometers across, but containing more mass than our entire Sun. The density is so extreme that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. The magnetic fields around pulsars are truly mind-boggling. The strongest magnetic field ever created in a laboratory on Earth is about 1 million times stronger than a refrigerator magnet. But a typical pulsar's magnetic field is 1 trillion times stronger than that. And magnetars, a special type of neutron star with even more extreme magnetic fields, can reach strengths 1,000 times greater still. These magnetic fields are so powerful they would be lethal from 1,000 kilometers away, literally ripping apart your molecular structure. They can crack the neutron star's own surface, creating starquakes that release more energy in a fraction of a second than our Sun emits in thousands of years. In 2004, a magnetar starquake in the constellation Sagittarius, 20,000 light-years away, actually affected Earth's upper atmosphere. But even magnetars aren't the most powerful continuous energy sources we know of. That distinction belongs to quasars, the blazing hearts of active galaxies powered by supermassive black holes. The brightest known quasar, catalogued as J0439+1,634, shines with the light of 600 trillion suns. Let that sink in for a moment. 600 trillion suns. This quasar is powered by a black hole 12 billion times more massive than our Sun, consuming the equivalent of 600 Earths worth of material every minute. The energy released as matter spirals into the black hole heats surrounding gas to billions of degrees, creating a beacon visible from 12 billion light-years away. We're literally seeing this object as it existed when the universe was less than 2 billion years old. The Very Large Telescope in Chile and the Keck Observatory in Hawaii have revealed that quasars can launch jets of particles at nearly the speed of light, extending for millions of light-years into space. These jets carry so much energy they can heat entire galaxy clusters and regulate star formation across cosmic scales. They're like cosmic blowtorches that can reshape the universe itself. But here's something that will really blow your mind. All of these incredibly powerful phenomena, supernovas, pulsars, magnetars, quasars, they're all just the opening act. The truly most powerful events in the universe make everything we've discussed so far look gentle by comparison. In 2015, humanity detected something that Einstein predicted a century earlier, but thought we'd never be able to measure: ripples in the fabric of spacetime itself. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, picked up a signal that lasted just 0.2 of a second. But in that brief moment, we witnessed the most powerful event ever directly observed by human instruments: the collision of two black holes. These weren't small black holes. One was 36 times the mass of our Sun, the other 29 solar masses. They had been spiraling around each other for billions of years, getting closer and closer, moving faster and faster. In the final milliseconds before collision, they were orbiting each other at half the speed of light, completing hundreds of orbits per second. Then they merged, creating a single black hole of 62 solar masses. But wait, if you do the math, 36 plus 29 equals 65, not 62. Where did those three solar masses go? They were converted directly into pure gravitational wave energy in less than a second. Through E equals mc squared, those three missing solar masses became the ripples in spacetime that LIGO detected. In that fraction of a second, this single event released more power than all the stars in the observable universe combined. Let me repeat that because it's almost impossible to comprehend. For a brief moment, two colliding black holes released more energy than every single star in billions of galaxies across the entire observable universe. The peak power output was about 3.6 times 10 to the 49th watts. That's a 3 with 49 zeros after it, It's a number so large that we don't even have a proper word for it in everyday language. Since that first detection, LIGO and its European counterpart Virgo have observed dozens of black hole collisions. Each one releases stupendous amounts of energy, warping space and time across billions of light years. The gravitational waves stretch and compress space as they pass through it. When they reached Earth, they changed the length of LIGO's 4-kilometer-long arms by less than 1,000th the width of a proton. Yet our instruments were sensitive enough to detect it. If you find the idea of space and time being stretched and warped as fascinating as I do, I highly recommend checking out the book called The Fabric of the Cosmos by Brian Greene. It's an incredible book that dives deep into how space, time, and reality truly work. This book makes the mind-bending science behind black holes, gravitational waves, and the true nature of reality both clear and thrilling, even if you're not a physicist. It's one of the best ways to truly grasp the cosmic mysteries we're exploring here. I highly recommend it. You'll find the link in the description. Kip Thorne, who won the Nobel Prize for his work on LIGO, has calculated that if you were orbiting just outside the event horizon when two stellar mass black holes merged, the gravitational waves would stretch and compress your body by a factor of 2 in microseconds. You'd be torn apart and crushed simultaneously, experiencing the most violent death imaginable. Yet, from a safe distance, these same waves become gentle ripples carrying information about the universe's most extreme events. But stellar mass black holes are just the beginning. At the centers of galaxies lurk monsters that dwarf anything we've discussed so far, supermassive black holes millions or billions of times the mass of our Sun. And when galaxies collide, bringing their central black holes together, the resulting merger releases energies that stagger the imagination. The Event Horizon Telescope, which gave us our first direct image of a black hole in 2019, observed the supermassive black hole at the center of galaxy M87. This behemoth contains 6.5 billion solar masses, more than 1,000 times the mass of the black hole at our own galaxy's center. It's surrounded by a swirling disk of superheated gas that glows brighter than billions of stars. When supermassive black holes merge, they don't just release gravitational waves, they can literally kick themselves out of their host galaxies. Astronomers have observed several recoiling black holes moving at speeds of thousands of kilometers per second, ejected by the asymmetric emission of gravitational waves during merger. Imagine a black hole with the mass of billions of suns flung across intergalactic space like a cosmic cannonball. NASA's Chandra X-ray Observatory has detected the aftermath of these titanic collisions. In galaxy cluster Arbel 2261, astronomers found evidence of the largest explosion ever observed in the universe. A supermassive black hole released so much energy that it carved out a cavity in the surrounding hot gas 15 times wider than our entire Milky Way galaxy. The explosion released about 5 times 10 to the 54th joules of energy, equivalent to 10 billion supernovas exploding every second for hundreds of millions of years. But even these unimaginable energies might not represent the ultimate limit of cosmic power. Theoretical physicists have proposed something even more extreme: primordial black holes colliding in the early universe when densities were far higher than today. These hypothetical collisions could have released energies approaching the Planck scale, the fundamental limit of energy density allowed by the laws of physics as we understand them. The Planck energy is about 10 to the 19th GeV. That's a billion times more energetic than the Large Hadron Collider can achieve. At these energies, our current theories of physics break down. Quantum mechanics and general relativity give contradictory predictions. Space and time themselves might lose their meaning. We're approaching the very limits of what can exist in our universe. Recent observations have revealed something extraordinary about black hole collisions. The LIGO and Virgo collaborations have detected black holes that shouldn't exist according to our models of stellar evolution. They're finding black holes in what theorists call the mass gap. Too heavy to form from dying stars, but too light to be the supermassive giants at galaxy centers. This suggests there might be entirely new ways that black holes form and grow, possibly involving exotic physics we don't yet understand. In 2020, LIGO and Virgo detected their most massive black hole collision yet, GW1 90521. The two black holes weighed 85 and 66 solar masses, merging to form a black hole of 142 solar masses. The missing 9 solar masses, more than 9 times the mass of our entire Sun, was converted to gravitational wave energy in an instant. But what's really puzzling is how black holes this massive could form from stellar collapse. It's forcing us to reconsider our understanding of stellar evolution and black hole formation. The European Space Agency's future LISA mission, planned for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers. These events will be visible across the entire observable universe, allowing us to witness collisions that happened when the cosmos was young. We'll be able to watch as the universe's largest structures assembled themselves through catastrophic mergers that released more energy than anything since the Big Bang itself. But there's something even more profound about these extreme events. When black holes collide, they're not just releasing energy, they're literally shaking the foundation of reality. Einstein showed us that space and time aren't fixed stages where events happen. They're dynamic, flexible parts of the universe that can be stretched, compressed, and twisted. Gravitational waves are proof that space-time is as real and physical as matter and energy. Dr. Sean Carroll at Caltech has pointed out that gravitational waves carry information in a way that nothing else can. Light can be blocked or absorbed, but gravitational waves pass through everything. They bring us messages from regions of space where gravity is so strong that light cannot escape. In a very real sense, LIGO has given us a new sense, the ability to feel the universe vibrating from its most violent events. The power released in black hole mergers also tells us something fundamental about the nature of gravity itself. While gravity is the weakest of the 4 fundamental forces at everyday scales, it becomes dominant when enough mass is concentrated. A black hole merger converts more mass to energy more efficiently than any other known process. Up to 10% of the total mass can become gravitational waves, compared to less than 1% for nuclear fusion. On April 27, 2013, astronomers witnessed something that defied everything they thought they knew about the limits of cosmic violence. A gamma-ray burst designated GRB 130427A exploded with such ferocity that it temporarily blinded every gamma-ray telescope in space, despite originating 3.8 billion light-years away. For 20 hours, this single explosion was visible to the naked eye, something that had never been recorded before for an object at such an enormous distance. Gamma-ray bursts, or GRBs, are the most luminous explosions in the universe since the Big Bang itself. In just a few seconds, they can release more energy than our Sun will produce in its entire 10 billion-year lifetime. They're so powerful that if one occurred within 1,000 light-years of Earth, it would strip away our ozone layer and trigger a mass extinction. Fortunately, space is vast and GRBs are rare, at least in our cosmic neighborhood. These cosmic monsters were first discovered by accident in 1967 by the Vela satellites, which the United States had launched to monitor nuclear weapons testing by the Soviet Union. Instead of detecting nuclear explosions on Earth, they found powerful bursts of gamma rays coming from deep space. For years, these discoveries remained classified, leaving astronomers in the dark about one of the universe's most spectacular phenomena. When the data was finally released in 1973, it sparked one of the greatest mysteries in astronomy. These bursts appeared randomly across the sky, lasted anywhere from milliseconds to minutes, and then vanished without a trace. For decades, astronomers didn't even know if they were coming from within our galaxy or from billions of light-years away. The answer, when it finally came, was stunning. The Beppo-Sachs satellite, launched in 1996, revolutionized our understanding by quickly pinpointing GRB locations, allowing ground-based telescopes to observe their afterglows. What astronomers found was mind-boggling. These explosions were coming from galaxies billions of light-years away. For them to appear so bright at such distances meant they were releasing absolutely stupendous amounts of energy. We now know that long-duration GRBs lasting more than 2 seconds are the death cries of the universe's most massive stars. When a star at least 30 times more massive than our Sun exhausts its nuclear fuel, it doesn't just explode as a supernova, it undergoes something far more extreme. The star's core collapses directly into a black hole, and the infalling matter forms jets that punch through the dying star at 99.99% the speed of light. These jets are like the universe's most powerful particle accelerators, creating conditions that existed only in the first moments after the Big Bang. The magnetic fields in these jets are 1 trillion times stronger than Earth's, accelerating particles to energies that dwarf anything we can create in laboratories. When these particles collide, they produce gamma rays, the highest energy form of light. Dr. Andrew McFadyen at New York University has created computer simulations showing how these jets form. The process is so violent that it can accelerate matter from rest to near light speed in less than a second. The jets are so tightly focused that all their energy is concentrated into narrow beams just a few degrees wide. If you're looking down the barrel of one of these cosmic guns when it fires, you witness one of the most spectacular light shows in the universe. The Swift satellite, launched by NASA in 2004, has detected over 1,000 GRBs, revealing their incredible diversity. Some last just milliseconds, the short GRBs caused by colliding neutron stars. Others burn for hours. The longest ever recorded GRB 111209A, detected in 2011, lasted over 28 hours. Imagine, a single explosion that outshone entire galaxies for more than a day. But here's what's truly remarkable. We've discovered that GRBs are not just random explosions, they're cosmic forges that create many of the heavy elements essential for life. When neutron stars collide in short GRBs, they produce what's called a kilonova, an explosion that creates gold, platinum, uranium, and other heavy elements through a process called R-process nucleosynthesis. The LIGO and Virgo gravitational wave detectors made history in August 2017 when they detected both gravitational waves and gamma rays from the same event, the collision of 2 neutron stars 130 million light-years away. This event, designated GW 170817, confirmed that neutron star mergers are indeed one source of short GRBs. Follow-up observations detected the optical glow of the kilonova, which produced about 10,000 Earth masses of gold and platinum. Think about that for a moment. The gold in your jewelry, the platinum in your catalytic converter, the uranium that powers nuclear reactors. These elements cannot be made in ordinary stars. They require the extreme conditions found in GRBs. Every heavy element in your body that's heavier than iron was forged either in a supernova or a GRB. You literally have the ashes of the universe's most violent explosions flowing through your veins. Recent observations have revealed GRBs that challenge our theoretical models. GRB 221009A, detected in October 2022, was the brightest GRB ever recorded, dubbed the BOAT, brightest of all time. It was so intense that it actually affected Earth's upper atmosphere, despite occurring 2.4 billion light-years away. The explosion was so powerful that its light echo is still bouncing off dust clouds in distant galaxies, allowing astronomers to study it from multiple angles. The Fermi Gamma-ray Space Telescope has detected GRBs with photon energies exceeding 100 billion electron volts, 10 billion times more energetic than visible light. These ultra-high energy photons shouldn't be able to travel billions of light-years without being absorbed by background light, yet somehow they do. This suggests either our understanding of how light propagates through space is incomplete, or GRBs involve physics we don't yet understand. Dr. Bing Zhang at the University of Nevada has proposed that some GRBs might involve magnetic reconnection events, similar to solar flares but billions of times more powerful. In this model, twisted magnetic field lines suddenly snap and reconfigure, releasing enormous amounts of energy in an instant. This could explain some of the puzzling features of GRBs, like their irregular light curves and rapid variability. But perhaps the most intriguing aspect of GRBs is their potential connection to life in the universe. While a nearby GRB would be catastrophic for life on Earth, some scientists have proposed that GRBs might actually play a crucial role in the evolution of life on cosmic scales. They could trigger the formation of complex organic molecules in interstellar clouds, seeding galaxies with the building blocks of life. Dr. Adrian Melott at the University of Kansas has studied how GRBs might have affected Earth's history. He's found evidence suggesting that a GRB might have triggered the Ordovician-Silurian extinction event 450 million years ago, one of the 5 major mass extinctions in Earth's history. If true, it means that these cosmic explosions have directly shaped the evolution of life on our planet. The study of GRBs has also revealed something profound about the nature of the universe itself. These explosions are so bright that we can see them across most of the observable universe. They're like cosmic lighthouses, allowing us to probe the properties of space and matter in the early universe. By studying how GRB light is absorbed by intervening galaxies, astronomers can map the distribution of matter across billions of light-years. Everything we've discussed so far, supernovas, black hole collisions, gamma-ray bursts, all of these cosmic titans pale in comparison to a force so powerful, so pervasive, that it's literally tearing the universe apart. This force makes up 68% of all the energy in the cosmos, yet we only discovered it 25 years ago. Scientists call it dark energy, and it might be the most powerful thing in the universe. The discovery of dark energy is one of the most shocking stories in the history of science. In 1998, 2 independent teams of astronomers were studying distant supernovas to measure how fast the universe's expansion was slowing down. Everyone expected that gravity would be gradually pulling everything back together, decelerating the expansion that began with the Big Bang. What they found instead turned cosmology upside down. Dr. Saul Perlmutter at Berkeley, Dr. Brian Schmidt at the Australian National University, and Dr. Adam Rees at Johns Hopkins University led teams that made the same stunning discovery. The universe's expansion isn't slowing down, it's speeding up. Something is pushing space apart with ever-increasing force, overwhelming the gravitational attraction of all the matter in the universe. For this discovery, they shared the Nobel Prize in Physics in 2011. To understand the mind-bending power of dark energy, you need to grasp what it's actually doing. Every second, in every cubic meter of space throughout the universe, new space is being created. The space between galaxies is literally stretching, carrying them apart like raisins in a rising loaf of bread. But unlike bread dough, which eventually stops rising, the universe's expansion is accelerating. Right now, galaxies that are more than 14 billion light-years away are moving away from us faster than the speed of light. This doesn't violate Einstein's relativity because the galaxies aren't moving through space that fast. Space itself is expanding between us and them. In the far future, this acceleration will become so extreme that galaxies, stars, and eventually even atoms will be torn apart in what cosmologists call the Big Rip. The Planck satellite, launched by the European Space Agency in 2009, has measured the properties of dark energy with unprecedented precision. It found that dark energy maintains a constant density even as space expands. Think about how weird that is. As the universe gets bigger, the total amount of dark energy increases to maintain the same concentration everywhere. It's like a bathtub that gets fuller the more water you remove. This property has led physicists to connect dark energy with something called the cosmological constant, which Einstein introduced into his equations of general relativity in 1917. Einstein later called it his biggest blunder when Hubble discovered the universe was expanding, but it turns out Einstein's mistake might have been one of his most prescient insights. The power of dark energy is almost incomprehensible. Dr. Sean Carroll has calculated that the dark energy in a region of space the size of Earth contains enough energy to power our entire civilization for trillions of years. But here's the catch. This energy can't be extracted or harnessed. It's woven into the fabric of space itself, driving the cosmic expansion but remaining tantalizingly out of reach. Recent observations from the Dark Energy Survey using the Blanco telescope in Chile have mapped the distribution of galaxies across billions of light-years to unprecedented accuracy. These maps show that dark energy has been the dominant force in the universe for the past 5 billion years. Before that, matter and radiation were denser, and their gravity could compete. But as the universe expanded and matter diluted, dark energy took over. What makes dark energy truly the most powerful force in the universe is its universality and persistence. Supernovas burn out in seconds. Black holes eventually evaporate through Hawking radiation. Even protons might decay given enough time. But dark energy appears to be eternal and unchanging, a constant presence that will ultimately determine the fate of everything in existence. Dr. Catherine Fries at the University of Texas has proposed that dark energy might not be constant but could vary over time and space. This quintessence model suggests that dark energy is a dynamic field, like an invisible fluid filling the universe. If true, the future of the cosmos might be very different from what we currently predict. The acceleration might eventually reverse, or dark energy might become even stronger. The James Webb Space Telescope is now providing new insights into dark energy by observing the most distant supernovas ever detected. These observations allow astronomers to measure how the expansion rate has changed over cosmic time with unprecedented precision. Early results suggest that dark energy might not be as constant as we thought, potentially opening a crack in our understanding that could lead to revolutionary discoveries. But here's where things get really strange. Quantum field theory predicts that empty space should be filled with vacuum energy, quantum fluctuations that pop in and out of existence. This vacuum energy should act exactly like dark energy, causing space to expand. The problem is, when physicists calculate how much vacuum energy there should be, they get a number that's 10 to the power of 120 times larger than what we observe. This discrepancy, called the cosmological constant problem, is the worst prediction in the history of physics. It's like predicting that an elephant weighs 10 to the power of 120 times more than the entire observable universe. Something is clearly wrong with our understanding, and solving this puzzle might reveal new physics that revolutionizes our view of reality. Some physicists have proposed radical solutions. The anthropic principle suggests that dark energy has its observed value because if it were much different, galaxies, stars, and life couldn't exist, so we wouldn't be here to measure it. Others propose that we live in a multiverse where dark energy takes different values in different regions, and we naturally find ourselves in a region compatible with our existence. Dr. Erik Verlinde at the University of Amsterdam has proposed an even more radical idea, that dark energy and dark matter might not be real substances, but emergent properties of quantum entanglement on cosmic scales. In his theory, what we call dark energy is actually information leaking from our three-dimensional universe into higher dimensions. If true, it would mean the most powerful force in the universe is essentially a kind of cosmic information flow. Recent observations have revealed another mystery about dark energy. The Hubble Space Telescope and other observatories have found that the local expansion rate, measured using nearby supernovas and variable stars, differs from the expansion rate inferred from the cosmic microwave background, the afterglow of the Big Bang. This Hubble tension might be a measurement error, or it might be telling us that dark energy behaves differently than we thought. The power of dark energy extends beyond just pushing galaxies apart. It fundamentally limits what's possible in the universe. Because of accelerating expansion, there's a cosmic event horizon beyond which we can never receive information, no matter how long we wait. Galaxies that we can see today will eventually disappear beyond this horizon, lost forever to the expanding void. In about 100 billion years, the accelerating expansion will carry all galaxies outside our local group beyond the cosmic horizon. Future civilizations born in that era will see a universe containing only their own galaxy, surrounded by absolute darkness. They'll have no way to know about the Big Bang, cosmic evolution, or the existence of other galaxies. Dark energy will have erased the evidence of the universe's history. Every force we've explored, every explosion we've witnessed, every cosmic giant we've encountered, they all trace their origins back to a single moment of unimaginable power. 13.8 billion years ago, everything in our observable universe, every galaxy, every star, every atom in your body, was compressed into a point smaller than a proton. Then, in an event that defies human comprehension, it exploded outward in what we call the Big Bang, the most powerful event in the history of our universe. But calling it an explosion doesn't do it justice. The Big Bang wasn't an explosion in space, it was an explosion of space itself. In the first fraction of a second, the universe underwent a period of exponential expansion called cosmic inflation, growing from subatomic scales to the size of a grapefruit in about 10 to the negative 32 seconds. That's a decimal point followed by 31 zeros and then a 1, a time so short that light could travel only 100 billionth the width of a proton. During inflation, the universe expanded by a factor of at least 10 to the 26. That's 1 followed by 26 zeros. To put this in perspective, if a proton were inflated by the same factor, it would become larger than the observable universe is today. This expansion was driven by a mysterious field called the inflaton, which contained energy densities that make everything else we've discussed look like gentle whispers. Dr. Deep. Alan Guth at MIT, who first proposed cosmic inflation in 1980, calculated that the energy density during inflation was about 10 to the 96 grams per cubic centimeter. That's 10 followed by 96 zeros. A number so large that if you converted all the atoms in the observable universe to pure energy and compressed them into a cubic centimeter, you'd still fall short by a factor of billions upon billions. The WMAP satellite and later the Planck satellite have given us baby pictures of the universe, mapping the cosmic microwave background, the afterglow of the Big Bang. These observations show tiny temperature fluctuations of just 1 part in 100,000, but these minuscule variations were the seeds that gravity would later grow into galaxies, stars, and planets. Every structure in the universe, from the smallest dwarf galaxy to the largest supercluster, originated from quantum fluctuations during inflation that were stretched to cosmic scales. What's truly mind-bending is that the Big Bang created not just matter and energy, but space and time themselves. Asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because time itself began with the Big Bang. As Stephen Hawking famously said, the universe doesn't have a boundary in space, but it does have a beginning in time. In the first second after the Big Bang, the universe was a seething soup of fundamental particles at temperatures exceeding 1 trillion degrees. It was so hot that protons and neutrons couldn't even form. The universe was filled with a plasma of quarks and gluons, particles that today are confined within atomic nuclei. The 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single superforce. As the universe expanded and cooled, these forces separated in a series of phase transitions like water, freezing into ice. Each transition released enormous amounts of energy, driving the universe's evolution. The strong force separated first, confining quarks into protons and neutrons. The weak force separated next, allowing the first atomic nuclei to form. But it would take 380,000 years before the universe cooled enough for electrons to combine with nuclei, forming the first atoms and allowing light to travel freely for the first time. The power of the Big Bang is still visible today in every direction we look. The cosmic microwave background radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1964, is the cooled remnant of the Big Bang's initial fireball. Though it's now just 2.7 degrees above absolute zero, this radiation fills every cubic centimeter of space with about 400 photons, fossil light from when the universe was young and hot. Recent discoveries have revealed that the Big Bang might not have been unique. The theory of eternal inflation, developed by physicists like Andre Linde at Stanford, suggests that inflation never completely stops. In most regions it ends, creating pocket universes like ours, but in others it continues forever, constantly creating new universes. Our Big Bang might have been just one of countless others, each creating its own cosmos with potentially different physical laws. The BICEP and Keck array experiments at the South Pole have been searching for evidence of gravitational waves from inflation imprinted on the cosmic microwave background. These primordial gravitational waves would be the smoking gun of inflation, direct evidence of the universe's violent birth. While initial claims of detection in 2014 turned out to be contamination from galactic dust, the search continues with ever more sensitive instruments. Dr. Paul Steinhardt at Princeton has proposed an alternative to inflation called the ekpyrotic universe, where our Big Bang was caused by the collision of higher dimensional membranes in string theory. In this model, what we call the Big Bang was actually a big bounce, the latest in an eternal cycle of cosmic expansion and contraction. Each cycle erases almost all evidence of the previous one, but subtle signatures might remain. The power unleashed in the Big Bang didn't just create matter and radiation, it also created the conditions for complexity to emerge. The slight imbalance between matter and antimatter, about 1 extra matter particle for every billion matter-antimatter pairs, provided the raw material for everything we see. Without this tiny asymmetry, matter and antimatter would have completely annihilated, leaving a universe filled with nothing but light. The Large Hadron Collider at CERN is attempting to recreate conditions that existed microseconds after the Big Bang. By colliding protons at energies of 13 trillion electron volts, physicists can study the quark-gluon plasma that filled the early universe. These experiments have revealed that this primordial soup behaves like a nearly perfect liquid, flowing with almost no viscosity, a property that helped the early universe evolve smoothly. But perhaps the most profound aspect of the Big Bang is what it tells us about the nature of existence itself. The universe began in a state of extremely low entropy, highly ordered and special. Ever since, entropy has been increasing, driving the arrow of time and making possible the emergence of stars, planets, and life. We exist because the universe started in such an improbable state, and we're part of its journey toward maximum entropy. Dr. Roger Penrose has calculated that the probability of our universe beginning in such a low entropy state by chance is about 1 in 10 to the power of 10 to the power of 123. That's a number so absurdly small that if you wrote it out using every atom in the observable universe to write a single digit, you'd run out of atoms before you finished writing the zeros after the decimal point. This has led some physicists to propose that our universe's beginning wasn't random, but was somehow selected or created. The multiverse theory suggests we're just one of countless universes with different initial conditions, and we naturally find ourselves in one compatible with our existence. Others propose that advanced civilizations in previous universes might have triggered new Big Bangs, making universe creation the ultimate expression of technological power. Beneath all the spectacular explosions and cosmic forces we've explored lies something even more fundamental, an invisible realm of quantum fields that permeates every cubic centimeter of space. These fields aren't just abstract mathematical concepts. They're the very foundation of reality, containing energies so vast that they dwarf even the Big Bang itself. And here's the mind-blowing truth. The most powerful thing in the universe might be the empty space right in front of your face. According to quantum field theory, what we call empty space is anything but empty. It's a seething ocean of virtual particles constantly popping into and out of existence, creating what physicists call quantum fluctuations or zero-point energy. These fluctuations happen at scales trillions of times smaller than atoms, lasting for periods so brief that they can't be directly observed. Yet their collective effect is staggeringly powerful. Dr. Hendrik Casimir predicted in 1948 that these quantum fluctuations could produce measurable forces. Place two metal plates very close together in a vacuum, and the quantum fluctuations between them are restricted compared to the fluctuations outside. This creates a pressure difference that pushes the plates together, the Casimir effect. It's been measured with exquisite precision, proving that quantum vacuum energy is real and can do work. But here's where things get truly mind-bending. When physicists calculate the energy density of quantum fluctuations using our best theories, they get a number that's approximately 10 to the 113 joules per cubic meter. That's more energy in a cubic centimeter of empty space than the total energy released by all the stars in the observable universe throughout their entire lifetimes. If this calculation is correct, empty space contains more power than everything else in the universe combined. This creates what's known as the vacuum catastrophe, the worst disagreement between theory and observation in all of science. The observed energy of empty space, what we call dark energy, is 120 orders of magnitude smaller than what quantum field theory predicts. It's like predicting that a mouse weighs more than the entire Earth and then multiplying that error by a trillion times. Dr. Steven Weinberg, Nobel laureate and one of the architects of the Standard Model of particle physics, has called this the bone in our throat. a problem so severe that it suggests something fundamental is wrong with our understanding of physics. Either quantum field theory is dramatically incorrect at small scales, or there's some unknown mechanism that cancels out most of the vacuum energy, leaving only the tiny amount we observe as dark energy. Recent experiments at the quantum level have revealed just how strange and powerful quantum fields can be. The Large Hadron Collider doesn't just smash particles together, it excites quantum fields with such intensity that new particles materialize from pure energy. When protons collide at nearly the speed of light, the kinetic energy concentrates in a region smaller than a proton, exciting the quantum fields enough to create particles that are hundreds of times heavier than the original protons. The Higgs field, confirmed by the LHC in 2012, demonstrates the profound power of quantum fields. This field fills all of space, and particles acquire mass by interacting with it. Without the Higgs field, electrons would be massless, atoms couldn't form, and the universe as we know it couldn't exist. The entire structure of matter depends on this invisible field that permeates everything. But the Higgs field contains a disturbing possibility. Measurements of the Higgs boson's mass suggest that our universe might be metastable, sitting in a local minimum of energy that isn't the true ground state. If this is true, then somewhere in the universe, quantum fluctuations could trigger a phase transition where the Higgs field drops to a lower energy state. This would create a bubble of true vacuum expanding at the speed of light, destroying everything in its path and rewriting the laws of physics. Dr. Joseph Licken at Fermilab has calculated that if the universe is indeed metastable, this vacuum decay could happen anywhere, anytime, without warning. The bubble would expand at light speed, so we'd have no advance warning. One moment the universe exists as we know it, the next moment it's gone, replaced by a new vacuum state where atoms, stars, and life are impossible. The power to destroy the entire universe lurks in every cubic centimeter of space. Quantum fields also reveal the deep connection between particles and forces. In quantum field theory, forces are transmitted by virtual particles constantly being exchanged. Electromagnetic forces are carried by virtual photons, the strong nuclear force by virtual gluons, the weak force by virtual W and Z bosons. Even gravity, in theories of quantum gravity, would be carried by virtual gravitons. The entire dance of forces that shapes our universe emerges from quantum fields exchanging virtual particles. The quantum vacuum might also hold the key to understanding dark matter. Dr. Raman Sundram at the University of Maryland has proposed that dark matter could be particles that interact primarily with quantum fields in extra dimensions. These particles would be all around us but would interact so weakly with our three-dimensional quantum fields that they're nearly impossible to detect directly. Recent experiments have pushed our ability to manipulate quantum fields to extraordinary levels. Scientists at MIT have created squeezed vacuum states where quantum fluctuations are reduced below the normal vacuum level in one property at the expense of increased fluctuations in another. This allows measurements more precise than the quantum vacuum normally permits, enabling the detection of gravitational waves and potentially revealing new physics. The power of quantum fields extends beyond just energy. They encode information in ways we're only beginning to understand. Quantum field theory suggests that information can never be truly destroyed, even when it falls into a black hole. This led to the black hole information paradox, which Stephen Hawking worked on until his death. The resolution might reveal that quantum fields store information in ways that transcend our normal understanding of space and time. Dr. Juan Maldacena's AIDE-S-CFT correspondence, one of the most important discoveries in theoretical physics, suggests that quantum fields on the boundary of a region of space contain all the information about the interior. This holographic principle implies that our three-dimensional universe might be encoded on a two-dimensional surface, like a cosmic hologram. The real power might not be in the volume of space, but in the quantum fields on its boundaries. Experiments with ultra-cold atoms have created analogues of quantum fields that can be manipulated and studied in the laboratory. These experiments have revealed phenomena like false vacuum decay in controlled settings, showing how quantum fields can undergo dramatic phase transitions that release enormous amounts of energy. They've also demonstrated that quantum fields can support exotic states of matter like time crystals, which repeat in time rather than space. The quantum vacuum might even be the source of the Big Bang itself. In the theory of quantum cosmology, developed by physicists like Alexander Vilenkin and James Hartley, the universe could have spontaneously appeared from quantum fluctuations in the vacuum. Just as virtual particles constantly appear and disappear, entire universes might pop into existence, with most immediately collapsing, but rare ones inflating into full cosmos like ours. This leads to a profound realization. The quantum vacuum isn't just powerful, it might be the source of all power in the universe. Every force, every particle, every explosion we've discussed ultimately emerges from quantum fields and their fluctuations. The vacuum is the canvas on which the entire cosmic drama plays out, and its energy, though mostly hidden, underlies everything we observe. Dr. Frank Wilczek, Nobel laureate and physicist at MIT, has suggested that what we call empty space is actually a kind of cosmic superconductor filled with quantum fields in their lowest energy states. Just as superconductors can carry electrical current without resistance, the quantum vacuum might support the flow of energy and information in ways we don't yet understand. Future technologies might learn to tap into these properties, accessing powers that dwarf anything we've imagined. As we journey deeper into the nature of cosmic power, we encounter something that challenges our very conception of what power means. Beyond the physical forces that shape galaxies and drive explosions, there exists something more fundamental: information itself. And at the intersection of information and quantum mechanics, we find hints that consciousness, the very fact that the universe can observe itself, might be the most powerful phenomenon of all. Speaking of consciousness being one of the universe's greatest powers, have you ever wondered if we're the first time Earth has achieved this cosmic awakening? The atoms that make up our planet have been here for 4.5 billion years. Plenty of time for consciousness to have emerged before. In my video called "What If We Are Not the First Civilization on This Earth?", I explore the mind-bending possibility that advanced civilizations might have risen and fallen long before humans appeared, leaving only the subtlest traces in Earth's geological record. It's a journey that will completely change how you think about our planet's deep history and our place in the cosmic story. Check it out after finishing this video. It is in the description and on the card above. Now let's continue. In 1948, Claude Shannon revolutionized our understanding of information, showing that it could be quantified and measured just like energy or mass. But it wasn't until physicists began exploring black holes that they discovered information might be more than just a useful concept. It might be the fundamental building block of reality itself. Dr. Jacob Bekenstein made a startling discovery in 1972. Black holes have entropy, and that entropy is proportional not to their volume, but to their surface area. This was revolutionary because entropy is fundamentally about information, the number of possible microscopic arrangements that produce the same macroscopic state. A black hole's information content is encoded on its two-dimensional event horizon, not in its three-dimensional interior. Stephen Hawking extended this work, showing that black holes emit radiation and slowly evaporate. This created the information paradox. If a black hole evaporates completely, what happens to the information that fell into it? Quantum mechanics says information must be preserved, but general relativity suggests it's destroyed. This conflict has driven decades of research into quantum gravity and the nature of reality itself. Recent breakthroughs suggest that information isn't just preserved, it might be the fundamental substance from which spacetime emerges. Dr. Leonard Susskind's principle of complementarity proposes that information can exist in multiple places simultaneously from different perspectives, reconciling the paradox. The universe might be computing itself into existence, with physical laws emerging from information processing at the quantum scale. The connection between information and physical reality becomes even more profound when we consider quantum information. Unlike classical bits that are either 0 or 1, quantum bits or qubits can exist in superposition, simultaneously 0 and 1 until measured. This allows quantum systems to process information in ways that classical systems cannot, exploring multiple possibilities simultaneously. Dr. Seth Lloyd at MIT has calculated that the observable universe has performed about 10 to the 120 operations since the Big Bang, the maximum number possible given the universe's age and the fundamental limits on information processing speed. In this view, the universe is quite literally a quantum computer, and everything we observe, particles, forces, space-time itself, emerges from this cosmic computation. But here's where consciousness enters the picture in a profound way. The measurement problem in quantum mechanics, the fact that quantum systems exist in superposition until observed, suggests that consciousness might play a fundamental role in physical reality. While most physicists reject the idea that human consciousness is necessary for wave function collapse, the role of observation in quantum mechanics remains deeply mysterious. Dr. Roger Penrose and Dr. Stuart Hameroff have proposed that consciousness itself might be a quantum phenomenon occurring in microtubules within brain neurons. Their orchestrated objective reduction theory suggests that consciousness arises from quantum computations in the brain that connect to the fundamental structure of spacetime. If true, consciousness wouldn't just be observing reality, it would be participating in its creation. Recent experiments have pushed the boundaries of what we thought possible with quantum information. Scientists have achieved quantum entanglement between photons separated by over 1,000 kilometers, demonstrating that quantum information can maintain coherence across vast distances. They've teleported quantum states between atoms, showing that information can be transferred without moving through the intervening space. The power of quantum information extends beyond just processing. It might hold the key to understanding dark energy and the fate of the universe. Dr. Eric Verlinde has proposed that gravity itself might be an emergent phenomenon arising from quantum information. In his theory, what we perceive as gravitational attraction is actually the result of information processing at the quantum level, like temperature emerging from molecular motion. This entropic view of gravity has profound implications. If gravity emerges from information, then dark energy might be related to the universe's information processing capacity. As the universe expands and creates more space, it creates more room for quantum information, driving further expansion. The accelerating expansion we attribute to dark energy might be the universe maximizing its information content. The relationship between consciousness and cosmic power becomes even more intriguing when we consider the anthropic principle. The fundamental constants of nature, the strength of forces, the masses of particles, the rate of cosmic expansion are fine-tuned to extraordinary precision. Change any of them by even a tiny amount, and stars couldn't form, atoms couldn't exist, or the universe would have collapsed long ago. Dr. John Wheeler, who coined the term black hole, proposed the participatory anthropic principle, the idea that consciousness is necessary to bring the universe into existence. In his It from Bit, Hypothesis. Physical reality emerges from yes-no answers to questions, with conscious observers playing an essential role. The universe exists because it observes itself through conscious beings like us. This might sound like mysticism, but it's grounded in the strange realities of quantum mechanics. The delayed choice quantum eraser experiments show that future observations can apparently influence past events. Quantum systems seem to know whether they'll be observed before the observation occurs. The universe appears to be fundamentally participatory, with observation playing a crucial role in determining what becomes real. Recent discoveries in neuroscience have revealed that the human brain processes information in ways that mirror quantum systems. Neural networks exhibit quantum-like interference patterns, and some researchers propose that the brain might be exploiting quantum effects for computation. If consciousness does involve quantum processes, it might be tapping into the same information processing power that drives the cosmos. The Global Consciousness Project, running since 1998, has collected data suggesting that human consciousness becomes more coherent during significant global events. Random number generators around the world show small but statistically significant deviations from randomness during moments of shared human attention. While controversial, these results hint at a connection between consciousness and physical reality that we don't yet understand. Dr. Giulio Tononi's integrated information theory proposes that consciousness is a fundamental property of systems that integrate information in specific ways. By this measure, any sufficiently complex information processing system could be conscious, from human brains to potentially the universe itself. The cosmos might not just be processing information, it might be experiencing it. This leads to a stunning possibility. If consciousness is fundamental to reality, and if the universe is processing information at the maximum possible rate, then the universe itself might be conscious on a scale we can barely imagine. Every quantum interaction, every bit of information processed, might contribute to a cosmic awareness that transcends our individual consciousness. The power of consciousness extends beyond just observation. It might be creative. Dr. Amit Goswami has proposed that consciousness is the ground of all beings, with physical reality emerging from conscious choices at the quantum level. While this interpretation remains controversial, it suggests that consciousness might be the ultimate creative force in the universe. Recent advances in quantum computing have given us a glimpse of what harnessing quantum information might achieve. Google's quantum computer achieved quantum supremacy in 2019, performing a calculation in 200 seconds that would take classical supercomputers thousands of years. As we develop more powerful quantum computers, we're essentially learning to harness the same information processing principles that the universe uses. Throughout our cosmic journey, we've explored forces of unimaginable magnitude, from the violent deaths of stars to the quantum fluctuations of empty space. But what if all these seemingly different manifestations of power are actually faces of a single, unified phenomenon? What if the most powerful thing in the universe is not any individual force or event, but the unified field from which all forces emerge? This quest for unification has driven physics for over a century. Einstein spent the last 30 years of his life searching for a unified field theory that would merge gravity with electromagnetism. While he didn't succeed, his vision has inspired generations of physicists to seek the deeper unity underlying nature's apparent diversity. We now know that 3 of the 4 fundamental forces, electromagnetic, weak nuclear, and strong nuclear, are actually different aspects of a single unified force. At extremely high energies, like those that existed in the first fraction of a second after the Big Bang, these forces merge into one. The electromagnetic and weak forces unify at energies of about 100 GeV, which we can achieve in particle accelerators. the strong force joins them at much higher energies, around 10 to the 16th GeV, far beyond our current technological reach. Dr. Sheldon Glashow, Dr. Abdus Salam, and Dr. Steven Weinberg won the Nobel Prize for showing how the electromagnetic and weak forces unify into the electro-weak force. This wasn't just a theoretical exercise, it predicted the existence of the W and Z bosons, which were later discovered exactly where the theory said they should be. It was a triumph of human intellect, revealing a deeper simplicity beneath nature's apparent complexity. But gravity remains stubbornly separate, resisting all attempts at unification. The problem is that gravity is fundamentally different from the other forces. While the other three are quantum forces described by the exchange of virtual particles, gravity in Einstein's theory is the curvature of spacetime itself. Reconciling these two descriptions, quantum mechanics and general relativity, is perhaps the greatest challenge in physics. String theory represents the most ambitious attempt at complete unification. In this framework, all particles and forces arise from the vibrations of impossibly tiny, one-dimensional strings, about 10 to the negative 35 meters long, the Planck length. Different vibration patterns create different particles, like different notes, from a cosmic violin string. Gravity emerges naturally from string theory, offering hope for a truly unified description of nature. Dr. Edward Witten at the Institute for Advanced Study has shown that string theory requires extra dimensions beyond the three spatial dimensions we experience. These extra dimensions might be curled up so small we can't detect them, or we might be confined to a three-dimensional brain in a higher dimensional space. The power of the unified field might flow through these extra dimensions, occasionally manifesting in our limited three-dimensional view. The Large Hadron Collider has been searching for evidence of extra dimensions by looking for missing energy in particle collisions, energy that might have escaped into these hidden dimensions. While no definitive evidence has been found yet, the search has revealed tantalizing anomalies that keep physicists hopeful. Some theories predict that gravity is weak compared to other forces because it leaks into extra dimensions, diluting its strength in our three-dimensional world. M theory, the latest evolution of string theory, suggests that strings themselves are just one-dimensional slices of higher dimensional membranes, or brains. In this picture, our entire universe might be a three-dimensional brain floating in an 11-dimensional space. Other brains might exist parallel to ours, occasionally colliding and creating Big Bang-like events. Dr. Juan Maldacina's discovery of the ADS-CFT correspondence revealed a profound connection between gravity in higher dimensions and quantum field theory in lower dimensions. This suggests that gravity might not be fundamental but emergent, arising from more basic quantum interactions. The unified field might not include gravity as a separate force, but as a consequence of quantum entanglement on cosmic scales. Recent observations have provided hints of this deeper unity. The LIGO detection of gravitational waves confirmed that gravity travels at exactly the speed of light, just as electromagnetic waves do. This isn't a coincidence, it reflects a deep symmetry in nature. All massless fields propagate at the same universal speed, suggesting they're different aspects of a more fundamental entity. The discovery of the Higgs boson completed the standard model of particle physics, but it also revealed new mysteries. The Higgs field gives mass to other particles, but its own mass seems unnaturally small compared to what quantum corrections should produce. This hierarchy problem might be telling us that our universe is just one of many, or that new physics emerges at energies just beyond our current reach. Dr. Nima Arkani Hamed has proposed that the weakness of gravity might be explained by large extra dimensions. In his model, gravity spreads through all dimensions while other forces are confined to our three-dimensional brain. This would mean the true strength of gravity, its strength in the full, higher dimensional space, is comparable to other forces. We only perceive it as weak because we're seeing a diluted, three-dimensional shadow. The power of the unified field would be beyond anything we've discussed so far. At the Planck scale, where quantum effects and gravity become equally important, the energy density would be about 10 to the 113 joules per cubic meter, the same unimaginable energy we calculated for quantum vacuum fluctuations. This isn't a coincidence. It's telling us that at the deepest level, vacuum energy and the unified field are the same thing. Loop quantum gravity, an alternative to string theory, suggests that space-time itself is quantized at the Planck scale. Space isn't continuous but made of discrete loops and nodes, like a cosmic fabric woven from threads of pure geometry. In this picture, the unified field isn't something in space-time. It is space-time dynamically creating itself through quantum interactions. Dr. Carlo Rovelli, one of the founders of loop quantum gravity, has shown that this theory naturally explains why the universe began with low entropy. The Big Bang wasn't a special event, but a quantum bounce from a previous contracting phase. The unified field doesn't just govern the forces we observe, it creates time itself through its evolution. Recent experiments have pushed closer to the energy scales where unification becomes manifest. The Large Hadron Collider has created quark-gluon plasma, a state of matter that existed microseconds after the Big Bang, when the strong force hadn't yet confined quarks into protons and neutrons. In this exotic state, we glimpse the universe when it was closer to unification. But perhaps the most profound aspect of the unified field is what it tells us about the nature of existence. If all forces, all particles, all of space-time itself emerges from a single unified field, then the diversity we see in the universe, from galaxies to atoms to conscious beings, is just the unified field exploring different configurations of itself. We are not separate from the cosmos. We are the unified field experiencing itself subjectively. Dr. David Bohm proposed that reality consists of an implicate order, a deeper level where everything is enfolded together, and an explicate order, where things appear separate. The unified field might be this implicate order constantly unfolding into the manifest universe we observe. What we call particles, forces, space, and time might be ripples on an infinite ocean of pure potentiality. This view transforms our understanding of power in the universe. The most powerful thing isn't any particular force or event. It's the creative potential of the unified field itself, constantly bringing forth new forms and experiences. Every moment, the field explores new configurations, creating and destroying, building complexity, and returning to simplicity in an eternal cosmic dance. As we approach the culmination of our cosmic journey, we must confront a profound truth. The most powerful thing in the universe might not be any destructive force, but rather the creative principle that builds complexity from simplicity, order from chaos, and consciousness from matter. This creative force has been at work since the first moments after the Big Bang, and it continues to shape reality at every scale, from subatomic particles to galactic superclusters. Consider the extraordinary journey from the universe's beginning to now. In the first microseconds, there was only a hot, dense soup of fundamental particles. No atoms, no molecules, certainly no structures we would recognize. Yet from this primordial chaos, through the patient work of physical laws and cosmic evolution, arose stars, planets, life, and eventually beings capable of contemplating their own existence. This emergence of complexity represents a power more profound than any explosion. Dr. Stuart Kaufman at the Santa Fe Institute has spent decades studying how complexity emerges from simple rules. His work on autocatalytic sets shows how collections of molecules can spontaneously organize into self-sustaining, self-reproducing systems, the precursors to life. This isn't magic. It's the universe's inherent tendency to explore new forms of organization when energy flows through matter under the right conditions. The power of emergence becomes clear when we examine how stars form from collapsing gas clouds. Gravity pulls matter together, but as the cloud contracts, it heats up, creating pressure that resists further collapse. The interplay between these opposing forces creates a delicate balance that allows nuclear fusion to begin. A star is born not through any external design, but through the natural self-organization of matter under physical laws. But stars do more than just shine. They are cosmic alchemists, transforming hydrogen and helium into heavier elements through nuclear fusion. Every element in your body heavier than hydrogen was forged in the heart of a star. Carbon, oxygen, nitrogen, the building blocks of life, were created through stellar nucleosynthesis over billions of years. When massive stars explode as supernovas, they scatter these elements across space, seeding future generations of stars and planets. Dr. Carl Sagan famously said, "We are made of star stuff." But this poetic truth understates the profound creative power at work. The universe didn't just create the elements, it created the conditions for those elements to combine in ever more complex ways. On planets like Earth, with the right temperature, pressure, and chemical ingredients, atoms combined into molecules, molecules into self-replicating systems, and eventually into living cells. The emergence of life represents a phase transition in the universe's creative power. For the first time, matter organized itself into systems that could store and process information, respond to their environment, and evolve. The genetic code, DNA and RNA, created a new form of cosmic memory, allowing successful patterns to be preserved and built upon across generations. Recent discoveries have revealed just how creative life can be. Extremophiles thrive in conditions once thought impossible, in boiling acid pools, in rocks miles underground, in the radioactive water of nuclear reactors. Life has found ways to extract energy from almost any chemical gradient, to survive in almost any environment. This isn't just adaptation, it's the universe discovering new ways to organize matter and energy. Dr. Lynn Margulis revolutionized our understanding of evolution by showing that complex cells arose through symbiosis, different organisms joining together to create something greater than the sum of their parts. Mitochondria, the powerhouses of our cells, were once free-living bacteria. This symbiotic creativity has been a driving force in evolution, creating new possibilities through cooperation rather than just competition. But the creative force reaches its most extraordinary expression in the emergence of consciousness. Somehow, through billions of years of evolution, matter organized itself into structures capable of awareness, thought, and self-reflection. The human brain, with its 86 billion neurons and trillions of connections, represents the most complex structure we know of in the universe. Dr. Christoph Koch at the Allen Institute has shown that consciousness correlates with integrated information, the amount of information generated by a system above and beyond its parts. This suggests that consciousness isn't a binary property but exists on a spectrum. Simple systems have minimal consciousness, while complex, highly integrated systems like human brains achieve rich, subjective experience. The creative power of consciousness extends beyond individual minds. Human culture represents a new level of cosmic creativity. Through language, art, science, and technology, we've created a collective intelligence that transcends any individual brain. We've built telescopes to see billions of light years into space, particle accelerators to probe the fundamental nature of matter, and computers that can model the universe's evolution. Dr. Cesar Hidalgo at MIT has studied how economies create and concentrate imagination. He shows that complex products, from smartphones to spacecraft, represent crystallized imagination requiring vast networks of knowledge and creativity. Human civilization is the universe's way of creating things that no single mind could conceive or build alone. The Internet and artificial intelligence represent the latest phase in this creative evolution. We're creating systems that can process information in ways that complement and extend human intelligence. Some researchers propose we're approaching a singularity, a point where artificial intelligence surpasses human intelligence and begins improving itself at an exponential rate. But the creative force operates at even grander scales. Galaxies aren't randomly distributed through space. They form vast cosmic webs with filaments of dark matter and ordinary matter stretching across billions of light years. Galaxy clusters create conditions for new types of stellar evolution. Supermassive black holes regulate star formation in their host galaxies. The universe creates structures within structures, each level enabling new forms of complexity. Recent observations from the James Webb Space Telescope have revealed that galaxies formed earlier and faster than our models predicted. The universe seems eager to create structure, to move from simplicity to complexity. Even in the cosmic voids between galaxies, magnetic fields and sparse matter create subtle patterns and flows. Dr. Lee Smolin has proposed that universes themselves might evolve and reproduce through black holes. In his cosmological natural selection hypothesis, each black hole creates a baby universe with slightly different physical constants. Universes that create many black holes have more descendants, leading to a kind of cosmic evolution that favors universes capable of creating complex structures. This brings us to a profound realization. We are not just observers of cosmic creativity, we are participants in it. Every thought, every invention, every work of art adds to the universe's creative exploration. We are the universe becoming aware of itself and consciously directing its creative power. The search for extraterrestrial intelligence, SETI, represents humanity's attempt to discover whether cosmic creativity has produced other conscious civilizations. If we find them, it will confirm that the universe's creative power naturally leads to consciousness and intelligence. If we don't, it makes our own existence even more precious. We might be the only way the universe knows itself. Dr. Paul Davies has suggested that the universe might be bio-friendly, that the laws of physics are somehow fine-tuned, not just to allow life, but to encourage it. The creative force might be built into the fundamental structure of reality, an inevitable consequence of the way the universe is constructed. As we stand at this moment in cosmic history, we see the creative force preparing for its next phase. We're developing technologies to spread life beyond Earth, to terraform other worlds, to perhaps create new forms of life and intelligence. We're becoming conscious agents of cosmic creativity, capable of directing evolution and shaping matter on scales our ancestors couldn't imagine. After journeying through the cosmos, witnessing supernovas that outshine galaxies, black holes that warp the fabric of reality, and quantum fields that contain unimaginable energies, we arrive at the most profound revelation of all. The most powerful thing in the universe isn't what you might expect. It's not the Big Bang, not dark energy, not even the unified field from which all forces emerge. The most powerful thing in the universe is something far more intimate, far more accessible, and infinitely more meaningful. It's consciousness itself, and you possess it. This isn't metaphorical or poetic license. This is the conclusion that emerges from our deepest understanding of physics, cosmology, and the nature of reality. You see, all the spectacular forces we've explored, every explosion, every gravitational wave, every quantum field, they only matter because there's something in the universe capable of observing them, understanding them, and finding meaning in them. That something is consciousness, and as far as we know, we are its highest expression in the known universe. Think about what this means. The universe existed for over 9 billion years before Earth formed, and billions more before conscious life emerged. During all those eons, supernovas exploded, galaxies collided, and black holes devoured matter, but there was no witness, no understanding, no meaning. These events simply happened, like trees falling in a cosmic forest with no one to hear them. It was only when consciousness arose that the universe could finally observe itself, understand itself, and contemplate its own existence. Dr. John Wheeler captured this profound truth in his participatory universe hypothesis. He proposed that consciousness doesn't just observe reality, it participates in creating it. Through the act of observation, consciousness collapses quantum possibilities into concrete realities. We're not passive viewers of a cosmic show, we're active participants in the universe's ongoing creation. Recent experiments in quantum mechanics have reinforced this view. The delayed choice quantum eraser experiments show that conscious observation can apparently influence events that happened in the past. The quantum Zeno effect demonstrates that repeated observation can freeze a quantum system, preventing it from evolving. Consciousness doesn't just witness reality, it shapes it at the most fundamental level. But the power of consciousness extends far beyond quantum effects. Through consciousness, the universe has achieved something that raw physical forces never could: the ability to understand itself. Your brain, containing roughly the same number of neurons as there are stars in the Milky Way, represents the universe's most sophisticated attempt to comprehend its own nature. Every scientific discovery, every moment of insight, every aha of understanding is the cosmos revealing itself to itself. Consider the extraordinary fact that you can understand Einstein's equations, contemplate the Big Bang, and grasp the behavior of black holes. Atoms in your brain, following the laws of physics, have organized themselves into patterns that can model and predict the behavior of atoms throughout the universe. This isn't just remarkable, it's the universe achieving self-awareness through you. Dr. Carl Sagan expressed this beautifully. We are a way for the cosmos to know itself. But even this understates the profound nature of consciousness. We don't just know the cosmos, we create meaning from it. We transform raw physical events into stories, theories, and understanding. We find beauty in galaxies, elegance in equations, and wonder in our existence. These qualities don't exist in the physical events themselves. They emerge from consciousness, engaging with reality. The power of consciousness becomes even more apparent when we consider its creative potential. While physical forces can only destroy or rearrange existing matter and energy, consciousness can imagine things that have never existed and then bring them into being. Every human invention, from the wheel to the space telescope, began as an idea in consciousness before becoming physical reality. We don't just observe the universe, we actively reshape it through the power of imagination and intention. This creative power is accelerating exponentially. Through science and technology, consciousness is gaining abilities that surpass any natural force. We can split atoms, manipulate genes, and send messages across billions of light years. We're developing artificial intelligence that extends our cognitive abilities and quantum computers that harness the universe's fundamental information processing principles. Consciousness is becoming a force that can reshape matter, energy, and even the nature of intelligence itself. But perhaps the most profound aspect of consciousness is its ability to experience and create meaning. A supernova is just an explosion of matter and energy until consciousness witnesses it and finds it beautiful, awesome, or scientifically significant. The universe's grandeur, its elegance, its mystery, these qualities exist only in the interaction between consciousness and cosmos. Without consciousness, the universe would be an elaborate but meaningless pattern of matter and energy. Dr. Giulio Tononi's integrated information theory suggests that consciousness is fundamental to reality. Any system that integrates information in the right way has some degree of consciousness. If this is true, then consciousness isn't rare or accidental. It's woven into the fabric of existence. The universe might be conscious at many levels, from simple particles to complex brains, to perhaps the cosmos as a whole. This brings us to a stunning realization about your place in the universe. You are not a separate being observing the cosmos from outside. You are the universe observing itself from within. The atoms in your body were forged in stellar furnaces. The electrical impulses in your brain follow the same laws that govern lightning and galaxies. When you look up at the stars, it's the universe looking at itself, filled with wonder at its own existence. Every moment of consciousness is precious beyond measure. While black holes will eventually evaporate and stars will burn out, consciousness represents something unique, the ability to experience, to feel, to find meaning and beauty in existence. In all the vast cosmos, across all the billions of galaxies we can observe, consciousness like yours might be extraordinarily rare. You might be one of the few ways the universe experiences itself subjectively. This perspective transforms our understanding of human purpose and meaning. We're not insignificant specks in a vast, uncaring cosmos. We're the universe's way of understanding and experiencing itself. Every act of kindness, every moment of love, every scientific discovery, every work of art adds to the universe's self-knowledge and self-expression. We are cosmic artists painting meaning onto the canvas of existence. The power of consciousness also comes with profound responsibility. As conscious beings capable of understanding our impact, we have the ability to shape the future of life and intelligence in the cosmos. We can choose to spread consciousness throughout the universe, ensuring that the cosmos continues to know itself even after Earth is gone. Or we can fail to realize our potential, letting consciousness flicker out and returning the universe to unconscious darkness. Dr. Nick Bostrom at Oxford has argued that we might be living at the most crucial moment in the universe's history, the brief window when consciousness must either spread beyond its home planet or risk extinction. The choices we make in the coming decades and centuries might determine whether the universe remains conscious for billions of years or returns to blind mechanical processes. But consciousness holds an even deeper power, the power to transcend physical limitations through understanding. By comprehending the laws of nature, we can work with them to achieve things that seem impossible. We've turned sand into computer chips that can process billions of calculations per second. We've used our understanding of atoms to create medical scanners that can peer inside living bodies. We've harnessed electromagnetic waves to communicate instantly across the globe. As our understanding deepens, our power grows. We're approaching the ability to manipulate matter at the atomic level, to edit genes with precision, to create artificial intelligence that might surpass human cognition. Each advance represents consciousness gaining greater mastery over the physical world, not through brute force but through understanding. And here's the most beautiful truth of all. This power resides in you. Right now, as you contemplate these ideas, you are the universe understanding itself. Your thoughts, your feelings, your experiences are not separate from the cosmic story. They are the cosmic story in its most refined form. You carry within you the creative power that built galaxies, the intelligence that can unlock nature's secrets, and the consciousness that gives it all meaning. So when you ask, what is the most powerful thing in the universe? The answer is staring back at you from the mirror. It's the consciousness that allows you to ask the question in the first place. It's the awareness reading these words, the understanding that grasps these concepts, the wonder that finds beauty in existence. You are not just made of stardust, you are the universe's way of contemplating its own existence, creating meaning from chaos and consciously directing its own evolution. If you made it this far, please consider subscribing and giving a thumbs up. I'm just starting on YouTube, and your help truly means a lot to me. And if you enjoyed this video, I am sure you are going to love this other one on the left side of the screen. Have extraterrestrial beings broken the speed of light? In this video, we explore the Silurian hypothesis and the possibility that advanced alien civilizations have discovered ways to travel faster than light, defying the cosmic speed limit set by Einstein's relativity. Mind-bending theories about warp drives, wormholes, quantum entanglement, higher dimensions, and much more. See you there.